Okay, so thanks for coming. Thank you for coming to the last second of the semester. But the last was great and also different times, so thanks for joining us today. So I would like to introduce now our speaker of the day, Professor Janardhan Padmanabhan. Jeremy, if you prefer, obtained PhD in 1991 from the Gujarat University in Hyderabad, India. Then as well for his inclusion of the field developer in Madison City for the following in 1993. Following the total of everything that was from the center. Science Academy. So I was a scientist together. For second contribution to the annual space program and space science. As you know, also, University of Maryland, and we were at the IC Institute in Maryland, and we for 3 times in University. Also, our minister, the Department of Math, and the physics in Cambridge, the other one. So,
Federico,
yes.
we cannot understand anything, via Zoom. The sound comes totally garbled.
Is it just so we can do something that we cannot minimize rules?
Everybody else that if you look at the chat, everybody that I don't know whether you need to hold the mic differently.
Yeah, is it better now?
We can hear you. We cannot understand what you're saying.
Maybe I got a microphone. Yeah, that's what we find out. So is that better? Is it better now? I feel microphone. Is this better?
It's a little better. It's still very difficult to understand. Sorry.
Okay. Other time by the hour, is that better? Well, let's see. So what about this mic? Can you hear better?
It's a little bit better.
Let's say let us know if possible. So,
Please fire.
okay. Thank you. So today we will talk about how we're going about solar. Thank you very much. Hello, am I audible? The people outside this room? Yeah.
Move it up.
Yeah, maybe if you can move it up. Or just. Yeah, okay. Hello, am I audible now?
Okay, so good afternoon, everybody. Thank you all for coming. It is indeed a pleasure for me to be here today to talk to you all. Okay. Right, let me know if this is okay. Good, right. Is that better now?
I think they're okay.
Yeah. Right.
Try saying.
Try to speak. Hello, can you hear me all? On the outside? Am I audible? Am I?
Nobody says anything. Try to speak.
Yeah.
Okay.
Yeah.
Okay, that was good.
Okay. So, okay, good afternoon, everybody. It's a pleasure for me to be here today, speak to you all. And right at the outset, I'd like to thank Dr. Fraschetti and Dr. Sachdev for putting a lot of effort and time in making this talk possible here today. So thank you for that. And I will be talking today about the question that is there as the title of my talk. Are we on the verge of a Maunder-Like solar minimum? And for those of you who are not quite familiar with solar astronomy, a Maunder-Like minimum is a extended period of time spanning several decades when the sun is completely devoid of sunspots. Okay, so that's what I'll be talking about. So let us begin with some brief history. It was Galileo Galilei who back in 1613 made the first significant statements on sunspots from his telescopic observations of the same. And basically he wrote about 3 articles in what was known as the Academy of the Lynx, which was the first scientific academy in the world, formed in 1603 in Rome. And they named it the Academy of the Lynx because the lynx was an animal with extraordinarily good eyesight, apparently. It's a wild cat. And they wanted the articles that they published to have the same deep, sharp insights into the whatever field of study they were writing about. So members of this society actually added a Lynxio to their name, as you can see here. And Galileo, in these 3 letters on sunspots, he said several things of importance. One, he said the sun is not perfect. It has spots. In those days, all heavenly bodies were supposed to be absolutely perfect, without any blemishes. Okay? And then he said the spots actually are on the surface of the sun. They dissolve back into the sun as they are carried around the sun. Now, in those days, the church took a very dim view on such beliefs, and you could in fact incur very severe punishment. You could be burnt at the stake, burnt alive for saying such things, because these were considered to be heretical statements. Thankfully, Galileo did not suffer those punishments because he was probably too well known at that point of time. Okay. The next big step forward came from this gentleman, Heinrich Schwabe. By profession, he was an apothecary, which is basically what we would call today a pharmacist. And he had a burning desire to become famous, to become well known. And he thought that the best way he could do that is by discovering another planet. In those days, in his time, 7 planets were known. And he was convinced in his mind that there was a planet orbiting the sun at a distance closer to the sun than Mercury was, that is inside the orbit of Mercury. And he thought it would be a simple matter for him to find that planet. And he had a name for it in his mind already. He wanted to call it Vulcan, after the Roman god of fire. And so he thought what he would do is simply observe the sun every day, on every clear day. And eventually any planet orbiting the sun would pass across, any orbit, any planet before the Earth would at some point of time pass in front of the disk of the sun, and it will be seen as a nice, beautiful dot against the bright disk of the sun. And shown here is an actual time-lapse image of the transit of Mercury across the sun in 2016, taken by the Solar Dynamics Observatory. So he observed for 17 years in this period, 1826 to 1843. He didn't find his planet, but after 17 years he gave up. But he wrote a book, Solar Observations during 1826 to 1843. And in that book, he claimed that sunspots actually vary with a period of about, sunspot numbers rise and fall with a period of about 10 years. And after that, he faded into the annals of history. Now, Rudolf Wolf, who we all know, he was the director of a solar observatory in Switzerland, Bern. He read Schwabe's book, was quite impressed, and so he gathered all of the data available and confirmed that indeed sunspots vary with a period of about 11.1 years, sunspot numbers. And I've shown here cycles 1 to 9. Wolf actually labeled the cycle starting in 1755 as solar cycle 1, because that was the first cycle that had a complete data set. Okay, so I've shown here 9 cycles, and the light green shaded area is the period when Schwabe observed. Now you will also see that cycles 5, 6, and 7 are kind of subdued as compared to the other cycles. And the famous British meteorologist John Dalton was studying aurora at that time, and he noticed a complete absence of aurora in this period. And he also simultaneously noticed that sunspot numbers were low. So he was the first person to make this connection between aurora and sunspots. And so this period is known as the Dalton Minimum, after John Dalton. Okay, and nowadays, whenever you have 3 or more cycles which are less than about 150 sunspots, which is that dashed line marked there, you call it some kind of minimum. Okay. And finally, about 120 years ago, George Hale discovered that sunspots were indeed regions of strong magnetic fields on the sun. Okay. So now we come to this young lady, Annie Scott de Maunder. She was working at the Greenwich Observatory in London. Very dynamic young lady. She was the first to photograph the sun, photograph the corona of the sun during eclipses. And she was also the first to draw the famous butterfly diagram of sunspots. She even made it all the way from England to India to observe an eclipse and photograph it in 1898. So that is the kind of person she was. And she noticed that this period 1645 to 1715, which you can see here, there were hardly any sunspots for about 70 years. However, in those days, women were not allowed to publish papers. Nor were they allowed to be awarded a degree. She came out at the top of her class in Cambridge in mathematics tripos, and yet she was not awarded a degree. And so her husband, Walter Maunder, who also worked at the Greenwich Observatory, published her work in his name. And therefore, this minimum is known as the Maunder Minimum instead of the Dill Minimum. Okay. That's it. There have been other minima in the past, like the Wolf minima, the Sporer minima, etc.
How do you have data for that period?
To gather it from historical records and from tree rings. There's carbon-14 data. You can measure the amount of carbon-14 in tree rings. And carbon-14 is formed when cosmic rays interact with nitrogen molecules in the upper atmosphere. So when the sun's magnetic field is weak, you have more cosmic rays, and therefore you have more carbon-14 formed in tree rings. So by measuring the amount of carbon-14 in tree rings, you can find the solar cycle independently. So that's how they did it. And with that method, you can go back some 10,000 years in time, depending on the tree you get. Okay. So what was important in this time, the Maunder minimum, both the Maunder and the Dalton minimum coincided with periods of global cooling. Okay. And however, some cooling during the Dalton minimum has been attributed to the eruption of Mount Tambora in Indonesia in April 1815. And Mount Tambora has been one of the strongest, most violent volcanoes in recorded history. It spewed about 45 cubic kilometers of material up into the upper atmosphere. And it caused the next year, 1816, was called a year without a summer because the sun was blocked out for large periods of time. Okay. Okay, so that is basically a very brief history of the observations of sunspots. Now here I've shown cycles 20 through 23, and you can see immediately that cycle 23 was much longer than the previous three. The dashed line is drawn at a sunspot number of 25, and you can see cycle 23 remained below 25 sunspots for a long period of time. And its period was about 12.6 years. It was an extended period. Okay. And you can see, you can plot the same thing in different manner. The bar chart on the left is, the green bars are actually showing sunspotless days in cycle 24 minimum. So you can see 274 sunspotless days in 2019. Okay. But the all-time record holder is 1913 when you had 311 or so sunspotless days. Right. Now, continuing with we are currently in solar cycle 25. So shown here is cycles 10 through 24. And that cycles 12, 13, and 14 is known as the Gleisberg minimum after Wolfgang Gleisberg, who first found it, first reported it in a publication. But what is interesting is not that, but take a look at cycles 21, 22, 23, and 24. The peak sunspot numbers are systematically coming down. Okay. So at this point of time, at the end of solar cycle 24, there was a lot of papers published kind of trying to predict what cycle 25 would be like. And the publications ran through the whole gamut. People said much stronger than cycle 24 or equal to cycle 24, less than cycle 24, and so on and so forth. And we also got into this game and we published one paper, and those were the numbers we had, which was roughly in the ballpark that this is. Okay. So 161 sunspots is what it peaked at in November of 2024. Okay. Now, because of this very steep decline in sunspot cycle numbers, we thought we would take a look at solar magnetic fields in more detail. And the data we used were basically from the National Solar Observatory at Kitt Peak and in the form of synoptic magnetograms. Okay. The sun rotates once in about 27 days, and each rotation is called one Carrington rotation. So we had from 1975 to 2009, 456 Carrington rotations of data for looking at magnetic fields on the sun. And we also looked at the solar wind. And we looked at the solar wind using what is called interplanetary scintillation. Okay. Now, interplanetary scintillation is basically the radio analog of the twinkling of stars in the night sky. stars twinkle in the night sky because of changes of refractive index in the neutral atmosphere of the Earth. And radio stars twinkle because of changes in electron density in the solar wind. So we used IPS data from 1983 to 2009, which was available from the Solar Terrestrial Environment Laboratory. At that time it was called STEL, now it is called ICE. So what we did was the following. Here is one Carrington rotation. I don't know which number actually. So just a sample Carrington rotation showing the magnetic fields on the sun for one full rotation. The red and the green patches are different polarities. And what we did is we averaged this Carrington rotation into in longitude to produce a 1 degree strip as shown in the right here. Okay. So this, and then we divided this 1 degree strip into various regions, 0 to 45 degrees north and south, we called it toroidal north and south, and 45 to 78 degrees, we called it polar north and south. And then we averaged the magnetic fields in each of these bins. So each strip gave us 4 points of data. And if you plotted those, this is what we got for the toroidal north and south regions, that is 0 to 45 degrees. Nothing surprising here. We see the solar cycle reproduced. But what was surprising to us was when we went to higher latitudes. The 45 to 78 degree north and south showed a steady decline in magnetic fields for this entire period to the end of the data set. So it raised the question as to what is going to happen next. Will this decline continue? Will it come up? And so on and so forth. And question is, does the decline continue beyond 2009? Okay. And that is the answer to that question. Goes all the way from mid-1990s, from the mid-1990s, and it's continuing to the present. This plot only goes to 2022, but it goes beyond, and what I have done is only shown published data. So beyond 2022, we have not published anything, but I know that it is continuing. So apart from a few blips here and there when it went a little above, it has continued. Right, so we had a huge kind of decline in solar magnetic fields. Now, when magnetic fields decline, like this is the same plot that I showed you earlier. When magnetic fields decline, cosmic ray flux goes up enormously because strong magnetic fields would deflect cosmic rays. And plotted here are solar cycle 23 and 24 cosmic ray intensities, and you can see that in 2024, the intensity was much more of the galactic cosmic rays in that energy range. Okay. Now, another thing that happens with cosmic rays is that the way they drift through the inner heliosphere or through the heliosphere is influenced by the what is called the heliospheric current sheet. The heliospheric current sheet is a region of space that divides the different polarities, the north and south polarities of the interplanetary magnetic field. So because the rotation axis and the magnetic axis of the sun are not aligned, this causes, when it rotates, the plasma gets distributed in something what they call a ballerina skirt model. So it looks like a ballerina skirt, and a cut across that skirt, it gives you what is called the heliospheric current sheet. And this angle typically is about 45 to 50 degrees in a regular solar cycle. It could go up as much as 70 degrees. But in 2020, okay, April of 2020, that is Carrington rotation 2030, the HCS tilt angle was only 2.1 degrees. That is, the heliospheric current sheet was basically flat. So a combination of the declining fields and the tilt angle of the heliospheric current sheet caused this to happen. Okay, and these tilt angles are available online. Okay. Right. The shown here is a diagram of how the Earth's magnetosphere looks from space. The red circle around the Earth is at 6.6 Earth radii, which is basically the geostationary orbit where we place all our geostationary satellites. And at 10 Earth radii, you have the magnetopause on the sunward side, and typically around 14 Earth radii is the bow shot. Okay, so what we found is that apart from the declining solar magnetic fields from sunspots, the solar wind dynamic pressure, which actually which actually maintains the sunward side of the magnetosphere of the Earth at these distances, the dynamic pressure has also decreased from January. This is a plot from 1995 to December 2017. So the black spots are from 75 to 1994, and you can see clearly that the solar wind dynamic pressure, the function of the polar field, has gone down. Okay. Now, if the dynamic pressure reduces, then of course the magnetosphere will expand outwards. And you can model the size and the shape of the magnetosphere. Okay. So what we do is there are a number of ways you can do this in the literature. And what we used is this Lu model, where you basically assume a priori functional form of the magnetopause. Okay, and that's the functional form. Theta is the zenith angle, and phi is the azimuth angle, and alpha and beta are parameters that can be determined using multi-parameter fitting between the functional form and solar parameters that you get from spacecraft. Okay, so if you do that, you can actually plot the shape of the magnetosphere in different years. Okay, so you can see this blue curve is 2020. This was published in 2019. So we were interested in predicting the size and shape of the magnetosphere in 2020. So this is in 2020, and this is the 95% confidence interval. Okay, so you can see that since 1996, which is that red curve, the magnetosphere has expanded outwards by 1 full Earth radii. Okay. Okay. So now let me come to the second part, looking at the solar wind. Now here is a schematic of a pictorial representation of a radio telescope observing a distant extragalactic point source through the inhomogeneous solar wind. Okay. Now this angle between the sun, the earth, and the source that is being observed is called the elongation angle. And if this angle is small, then this line of sight is passing close to the sun. As if you look at stars far away, then the line of sight is far away, and this distance r changes. So r is the perpendicular distance from the sun to the line of sight. And because the scattering function goes as r to the -4, most of the contribution to your scintillation will come from a region around the point P, which is the shortest distance from the line of sight. Okay. So this is a method by which you can probe the solar wind and look at it in slightly more detail, because you're looking at a point source that is infinitely far away. You're basically getting plane waves from that source. And that illuminates this inhomogeneous solar wind, which is assumed to be confined to a thin screen of thickness L and having scale sizes of, say, A. And after these plane waves pass through this solar wind, it picks up an RMS phase deviation because of changes in the electron density distribution. So once that happens, at the bottom of the thin screen, you have a a wave which has imposed on it an RMS phase deviation. And such a wave is known as a wave with a complex amplitude. Okay? Now, complex amplitude and angular spectrum have a Fourier transform relationship. That means that this picture and this picture are identical. So you can view this as a single wave with an RMS with a complex amplitude, or you can view it as large number of plane waves traveling in different directions at different angles to that original direction. So if you viewed it, if it is equivalent to large number of plane waves traveling in different directions, then at some point of time, these plane waves will propagate and add or cancel out depending on phase. And then those phase deviations will get converted into intensity fluctuations, which is what we call scintillation. Okay, so here is an extragalactic radio source 0138 plus 136. As observed at 327 megahertz from India with the UT radio telescope. And this is how it looks when you're observing a blank part of the sky with no source. So this is an off source and on source. So at 327 megahertz, this line of sight can go as close to the sun as 12 degrees and as far away as 55 degrees. And you will be then probing the solar wind at a distance range of 0.2 to 0.8 of an AU, which is almost the entire inner heliosphere. Okay. What we measure actually is called the scintillation index, which is basically the scintillating flux divided by the mean source flux. Okay. So these extragalactic radio sources generally have a compact component, and they are surrounded by a kind of diffuse halo. So the flux in the compact component is what we be coherent. And so that is called the scintillating flux. And the mean source flux is from the whole radio source. So in what we call the thin screen approximation, which I talked about, this scintillation index is basically given by √2 times the RMS phase deviation imposed on the wave. And phi RMS itself is proportional to the RMS delta n. Okay, the RMS electron density fluctuations in the solar wind. All other quantities are constants. Lambda is the observing wavelength, Re is the classical electron radius, A is the scale size, and L is the thickness of the screen. Okay. So if you theoretically estimate how this scintillation index is supposed to behave as a function of distance from the sun, this is how it is. For each, this MAS stands for milliarc second. So for an ideal point source, which is 0 milliarc seconds in angular width, you will get this black curve, and for the bottommost green curve is for 500 milliarc seconds. And at 327 megahertz, as I said before, it can range from 0.2 to 0.8 AU. And these are two radio telescopes in India. This is called the UT radio telescope. It's not a dish, I call it a dash, because it is 530 meters long and 30 meters wide. Okay. And it is built on a mountain slope. And that slope is equal to the latitude of the place. So when you build a telescope angled in such a manner, then the axis of rotation of the telescope becomes parallel to the axis of the Earth. So this rotation axis of the telescope is basically...
The seminar, yes.
No, I'm going to go to Trader Joe's.
Yeah, is there a question?
No, sorry.
Yeah. So this axis is like the axis of the Earth, and so you can rotate the telescope with just one motor east to west. Okay, and you can actually track a source from the time it rises to the time it sets. And you can point the beam in different directions by using phase differences in the cables. So that's called the UT radio telescope. It was built in 1969. And at that time, the first pulsars were discovered in 1967, and there was big hurry to try and find new pulsars at the time. So the telescope was not fully completed, but they were in a hurry to find some of these new pulsars. So they observed before the telescope was completely built, and the telescope collapsed. So they had to build it again, and it took another 2 to 3 years. And by the time it came up again by the end of 1972, most of the strong radio pulsars in the sky had already been discovered. So it was a pity. And this is the below is a regular dipole array that we built during my PhD at PRL. It had an area of 20,000 square meters, and it operated at 103 megahertz. In those days, we did not have FM radio in the state of Gujarat. And 103 megahertz is right in the middle of the FM band. But that's the only frequency at which we got the license from the government. So we anyway went and built the telescope, and it lasted for about 10 years before FM stations started coming up. And it destroyed our IPS telescope due to radio interference. Okay, just a little digression here, because it was IPS that led to the discovery of pulsars. You know, Jocelyn Bell Burnell, who worked with Professor Anthony Hewish from Cambridge, they were doing regular IPS observations, and she noticed what she called a bit of scruff, quote unquote. But it looked exactly like radio interference that can come from a factory or from cars, spark plugs, and so on. But what she noticed amazingly was that this little bit of scruff appeared on the chart recording 4 minutes earlier each day. That means it was not a local radio interference, but it was coming from the sky. So what they did was they ran the chart recorder at high velocity, high speed under the pen, and this scruff resolved itself into these pulses. So this was the first ever pulsar found, and this was the first periodic signal received from space. And so they thought that some extraterrestrial civilization was trying to contact the Earth. And therefore they called this LGN, Little Green Men. Okay? And this was Little Green Men 1, 1919 plus 21. But very soon they found the second one, and the third one, the fourth one. So immediately they could rule out that it was not Little Green Men, because you can't have 4 extraterrestrial civilizations trying to contact you at the same time. And Anthony Hewish, who is shown here in the upper picture, he actually went on to write a paper and show that such signals could be created by a neutron star, which is rotating. And every time and neutron stars emit radiation only from the poles. And so when that sweeps across the Earth, you get a pulse. So it's like a very heavy flywheel spinning in space. And he received the Nobel Prize for that. There was a lot of controversy of why Jocelyn Bell was not part of that Nobel Prize. And she had also visited PRL in 2014, gave a fantastic lecture. So that was just a little bit of digression. So coming back, we know how the scintillation index is supposed to behave as a function of elongation. And these are some actual data from the UT radio telescope at 327 megahertz. And this straight line, the dotted line is not a straight line fit. It is one of these templates. So it is the best possible template that will match this data. So you can see 1148 minus 001, the black curve matches it best. This is 0138, which I just showed the scintillation from. That corresponds to 250 milliarc seconds. In fact, when Anthony Hewish and Jocelyn Bell made their telescope in Cambridge, the idea was to measure angular sizes of radio sources using this method. Because at that time, 1963, the first quasars were discovered, and nobody knew what these things were. So they were billions of light years away, but they were extraordinarily strong at almost all wavelengths. And so the idea was to understand what these were. That's why they were called quasars, in fact. So instead of that, they actually discovered pulsars, which was a good thing. Sometimes serendipity is a good thing. And if you want to make a large number of such observations and compare between them, you cannot do it directly because there are two things that are varying here. The source size is varying, the scintillation index is falling off with source size and with distance. So you have to normalize this data in some manner so that you can eliminate one of these. And what we do is we normalize all the data by point source. And when you do that, you remove the distance dependence. Okay? So now you have a set of data that is only dependent on the source size. Okay? And you can plot that. And this is what you get. Okay? So the scintillation index also drops off with almost the same slope as the magnetic fields on the sun. I've shown both of these together. And the natural thing to do is to extrapolate that straight line and ask, when will it go to zero? And both of them, because they have the same slope, will of course go to zero around the same time. And so it means that this decline in the magnetic fields is on the sun, is affecting the solar wind dynamic pressure, and the micro-turbulence in the solar wind in a similar manner. Okay. Now we have data up to about 2034, up to that, not 2034, up to that point shown by these arrows, which is something like 2022, 23. And this decline is continuing right up to that time. Again, because this has not been published, I have not actually shown it here. Okay. So now we have shown that solar photospheric magnetic fields and solar wind microturbulence levels are both declining at the same rate. Many people tried to model the onset of a grand minimum and asked, a Maunder minimum is also known as a grand minimum. And they went back looking at tree rings to reproduce past solar cycles using carbon-14. And they found that in the past 11,000 years, you can identify 27 grand minima have occurred. Okay? So, which means that these are not what it means is that sun can be forced into a grand minimum if certain conditions are met. Okay? So, if you assume that each of these grand minima lasted around 70 years, like the Maunder minimum, then it means that roughly 17% of its time, the past 11,000 years, the sun spent in grand minima. Okay. Now they also found that 1 or 2 cycles before grand minima onset, the cycle period becomes longer. Okay. That is a paper by Karak and Chaudhary. And there is also evidence for longer cycles before the start of the Maunder and the Sporer minimum. And we have seen a lengthening of the cycle in cycle 23. Okay. Supporting that. And finally, fluctuations in meridional circulation initiate grand minima, with gradual changes giving rise to a gradual onset. Okay. So this is a paper from Hathaway and Whitemere where they actually measured through the entire solar cycle 23 the meridional circulation. So on the sun, you have flux being transported to the poles via a weak meridional circulation flow that is about 10 to 15 meters per second. And flux is also transferred around the sun in azimuthal direction. Okay. So this meridional flow is what carries flux to each of the poles, and at the peak of every solar cycle, it reverses the polarity, cancels out the existing flux, and a new polarity is formed. So the sun flips its poles every 11 years at solar maximum. Okay? So the meridional circulation plays a very important role in that. And finally, weak polar field or weak meridional circulation, or both, can cause the onset of grand minima. Okay? Now, here on the above panel, you saw the meridional circulation going from 11 to 8 to 13 meters per second. And recent work from PRL has used full disk radio images of the sun and to look at radio bright features. So if you use a large number of full disk images from the Nobuyama radio heliographs, you can actually determine the meridional flow, and the black is in cycle 24 and the pink is in cycle 23. And you can see that, let us say at a particular latitude, typically the meridional flows are much weaker than expected. Okay, in the northern hemisphere, in fact, it is just under 5 meters per second, and the southern hemisphere it's about 8 or 9. Typically, these values are around 15 meters per second. So the meridional circulation is weak, polar fields are weak, the solar cycle lengthened before this happened. So all of the conditions that seem to create grand minima seem to be there. And so that raises the question, are we headed towards a grand solar kind of minimum? So this is not directly related with grand minima, because I was the PI of an instrument on India's Aditya mission. I would just very briefly talk about our instrument. So our instrument is called the Aditya Solar Wind Particle Experiment, or ASPEX. And it measures particle flux from 100 eV to 5 MeV using multi-directional observations. It was entirely designed and developed at PRL and is one of 7 payloads on board Aditya. Aditya was launched in 2023 September, and it reached L1 point 6th of January 2024. And science observations actually began from around March, April of 2024. So now we have about 2 years of observations with Aditya. Now, the solar wind, both fast and weak, energy-wise, they end at around 3 kilo electron volts. Okay, so the solar wind doesn't go much beyond that, except when you have CMEs and stuff. And suprathermal ions, which represent these energies beyond 20 keV, they continuously arrive at the spacecraft from all directions in the solar wind. Okay, so that is Aditya, and you can see our experiment sitting there, this is called SWISS, and the other one below here is STEPS. SWISS is the low energy part. It comprises 2 top hat analyzers, okay, to measure from 100 eV to 20 keV. And beyond that, STEPS is detectors, which are silicon pin detectors, which measure in multi directions. So you have a north pointing detector, a Parker spiral detector, an intermediate detector, and a sun radial detector, along with south pointing and earth pointing. Okay, so here is some data from SWISS ASPEX solar wind ion spectrometer as compared to the instrument onboard wind spacecraft called PISA, which is the proton electrostatic analyzer low. And that goes from 100 eV to 10 keV, and now it goes from 100 eV to 20 keV. And you can see that both the data sets are almost identical. Okay. In fact, the separation between alpha and protons is much better in ASPEX. And this is from STEPS. I'm showing you this just as a comparison. The uppermost and lowermost panels are from the ACE spacecraft, the ACE EPAM and the ACE ULIS. And the middle panels are from STEPS, intermediate, north pointing, earth pointing, and Parker spiral. And they're all comparable. This is in February of 2024. Now, if you take quiet time solar wind data, and there's no flares or CMEs and things, and you can derive their spectra. Okay, and if you take the linear part of the spectra, this part is actually affected by what we call the LLD. LLD is a low-level discriminator in the electronics of the system that tries to remove the noise created by the electronics itself. So at the output of the LLD, it's only at the output of the LLD that the spectra will become kind of linear. So we ignore this part. Okay, and if you fit these spectra with straight line fits, you can derive a spectral index for each of the detectors. PS is Parker spiral, intermediate, earth pointing, north pointing, etc. And if you, this another point. Now, acceleration of suprathermal ions in the IPM generally uses what's called the Parker transport equation. And this assumes that these suprathermal ions in the solar wind are isotropic. Everybody has been assuming that it's isotropic, but no measurements in situ have actually shown it is isotropic. But this is the first time we have detectors pointing in different directions in space. And so you can plot all of them. You can see that's the Parker spiral, intermediate, earth pointing, and north pointing. And all the spectral indices fall within a small range with an average of nearly -2. So what it means that these are the first multidirectional observations to show that the solar wind suprathermal ion flux is indeed isotropic. Okay? And this was recently published, 2025. Okay. So I'll stop here with, I do some bird photography at times when I have spare time. And Vikram Sarabhai is the person who created India's space program. And he also founded the Physical Research Laboratory and is so very amazing person. And he used to say that it is necessary in creative work to be able to see squirrels and birds. And so I thought it would be appropriate to put a photo of a bird here as the last slide. So thank you all for your attention. And before I end, I would like to, that was my ASPEX team, bunch of young engineers. And they did a wonderful job. So I'd like to end this talk by thanking them too. Thank you very much. I hope I've not exceeded the time by.
Oh, perfect on time.
Okay.
Thank you.
Yes. Are there any questions?
Let's see. Do we have any questions? I'm sorry, I just said, maybe let me start. I was curious. So you mentioned that 17% of the time the sun is in granular. So during that study, there is any periodicity in this granular?
No, they couldn't find the periodicity because I think we need much more than 1,000 years. So let's see. People have tried. There are some papers I can share the link with you that try to there is some kind of a 1,000-year periodicity.
Okay. Thanks. Let me see what people think about the questions. See, no here.
Thank you for the talk. It was really interesting. I was wondering, it seemed like there are so many different ways to measure solar activity. And the two that you did the particular linear fit being the magnetic field strength and the scintillation index, but they seem quite related, of course. So I was wondering what kind of independent measures of solar activity might there be?
If you want to see a large scale picture, then you have to take long-term data. Okay. If you want to see kind of snapshot, and circulating index, if you use a very large number of sources observed at the same day, supposing you look at 500 sources in the sky in one day, then you plot delta n in that day. So that's a 1 day snapshot of the solar wind. So it's like having a camera with a shutter speed of 1 day. You can go down to half a day or so. But in situ measurements are the best way to, if you correlate, say, in situ measurements from space with radio measurements from the ground. There's no direct way of getting an overview. Long-term observations is what I can do. Which is why observations in situ of things like CFAs and flares are important. But if you do that for a sufficiently long period of time and somebody takes the trouble to see overall what is that telling you, that picture is not yet emerged. Broadly, yes, but let's see. For example, there have been periods of time in the solar wind when solar wind streams have completely disappeared. Solar wind disappeared. Okay? The solar wind density is 40.1 particles per cc. Now, a typical value of 10 particles per cc, and it persists for more than 24 hours. Okay? We don't understand this, or we did not understand this for a long time. We were the first to actually show what is happening on the sun during this period. So it's a case by case kind of story. I don't know if my answer is satisfied your question, but so that's that. So, we have a question on the line. How do you want to speak up and ask the question? And so the question is, we have a common minimum. So, for interpretation. If cycle 25 had been kind of equal to 24, then I don't know. We have to see how the next cycle develops. If the next cycle also is kind of weak, then I'm more or less sure we'll show Maunder-Like. And that would be the first time in recorded modern history that it's happened. Be interesting if it happens. But if it doesn't, also, that would still be interesting. But all the signs are there that something peculiar is happening. In fact, if you look at other peculiarities, which I have not had time here, may I just show a couple of other slides? Let's. This is the way the polar field reversed in cycle 24. The southern hemisphere reversed in November 2013, but the northern hemisphere remained at zero for 2.5 years before it reversed. So something is happening on the sun that is not okay. And if you looked at solar wind measurements, solar wind velocities, now the solar wind generally, the polar regions are open magnetic field lines. So the plasma flows out freely from there. So you have very high velocities at the poles. Okay, so this blue in the lower panel are the high velocities. And the upper one, you do not see a polar coronal hole at all. Okay. So upper panel was in 2015 and then 2016. So peculiar things are happening both in the solar wind and on the sun. So something is brewing. We don't know exactly what. Okay. Very more questions. I see none. I'm just curious about something that you were showing in the photospheric magnetic field time decay. There was a single band, which I don't know if does correspond to any particular.
No, we tried to look at nothing particular because each point there takes 1 year to make.
Yes.
Okay, and there's some fluctuations. I don't know why that happened. It didn't persist. It lasted just 1 year or 2 years at the
Was that
maximum.
one hole?
Yeah, then it came down.
Okay, all right. So if we have no questions, now let's thank Janardhan. Yeah. And since we got the last seminar of the semester, maybe sure, we have more seminars of course special during the summer, but that's the fifth and last.
Yeah.
Thank you so much.
Thank you all for attending.